Hi again. So until now, we talked about counting binary sequences, specifically binary sequences of length n with k1s. And now we want to grow up a little bit. Instead of binary sequences, we want to move to sequences of a larger alphabets. For example, ternary sequences, or sequences of alphabet of size 4 or so. So, and to do that, we're going to use, instead of binomials, we're going to use multinomials, but don't worry, it's actually a very simple extension. Okay. So going to talk about the multinomial coefficients, which beyond binary, they apply for ternary or larger alphabet stiles. Okay, so for example, if we're going to look at ternary alphabets, then imagine that we have three numbers, k1 plus k2 plus k3, which together gives us n. This extends what we had before, where we had k1s and n minus k0, so now we have maybe k1s and k2s and k3s. And together they give us the whole length of the sequence, which is n. Okay, so we're interested in the number of sequences over 1 to 3s, sequences with 1, 2, and 3 of length n, with exactly these numbers, k11s, k22s, and k33s. And because of that, as we have said, these ki's have to sum to n, because the sequence will have all the n elements are going to be either 1s or 2 or 3s. Okay. And we ask how many such sequences are there. So the number of such sequences, to count it, we can just apply the binomial theorem twice. So we can say, well, we need to choose the location of the ones, and we have n locations, and we have to choose k1 ones. So the number of ways to do this is n choose k1, that we have seen in the previous lectures. Okay. And after we chose the location of the k1 ones, we're left with n minus k1 locations, right? And from those n minus k1 locations that are left, we need to choose the locations of the k22s. So we need to multiply it. So this k1's locations of the ones, and then we have n minus k1 locations left, and we need to choose k2. So this is k2 locations of the 2's out of the n minus k1's locations of that are left. Notice that once we choose those 1's and 2's, then the location of the 3's are determined because we have k1 1's and k2 2's, and then we're left with now n minus k1 minus k2 locations, but all of those have to be the k3 3's that are left. So this is exact number. If you wanted to multiply it, you could also multiply it by n minus k1 minus k2, choose k3, but observe that n minus k1 minus k2 is k3. So what you'd have is k3, choose k3, which is 1. So this is the total number. Again, we chose k1 locations of the ones. That's n choose k1 different ways of choosing those locations. And then we're left with n minus k1 locations for the 2's and the 3's. We need to choose the location of the k2 2's. We have to do it in n minus k1 choose k2 ways. So when we multiply them, we get a total number of ways of choosing the 1's and the 2's, and that will determine the 3's. So now what we need to do is just write this out as a product of factorials. So this is equal to n factorial divided by k1 factorial n minus k1 factorial. And then we need to multiply by this binomial coefficients, which is n minus k1 factorial divided by k2 factorial and n minus k1 minus k2 factorial. And we have some cancellations here, because we have here n minus k1 factorial cancels with this. Okay, let's see. And then we observe that n minus k1 minus k2 is just k3, because the ki is summed to n. So that means the total number is n factorial divided by k1 factorial, k2 factorial, k3 factorial. And we denote this by the multinomial coefficient n choose k1, k2, k3. So again, n choose k1, k2, k3 is the number of sequences of length n with k1 1's, k2 2's, and k3 3's. And it's equal to n factorial divided by k1 factorial, k2 factorial, k3 factorial. And you notice a couple things. You notice how nicely it generalizes the binomial coefficients, which was n factorial divided by k1 factorial and k, say, 2 factorial. Okay, so now we just have this product of the 3, and you also notice that it's symmetric with k1, k2, k3, as we would expect, because it's just number of sequences with k1 1's, k2 2's, and k3 3's. Okay, so this is the multinomial coefficient, and the only one thing I want to mention is that we're using a slightly different notation than we use for the binomial coefficients. So the binomial coefficients we use n choose k, but if we use the same convention here, then we would denote it by n choose k and n minus k, and still be the same. It would be n factorial divided by k factorial. And again divided by n minus k factorial. So this is a different special case that for binomial coefficients we just use this instead of writing both the number of zeros and the number of ones. Okay, all right. And as we said, these sum to n as they would here. All right. So let's do a simple example. How many sequences are there over 1, 2, 3, 4? So instead of alphabet of size 3, we're looking at alphabet of size 4. Where the digit 1 appears once, the digit 2 appears twice, 4 times, the digit 3 appears 4 times also, and the digit 4 appears twice. So the length is 1 plus 4 plus 4 plus 2, which is 11. Okay, and one example of such sequence is 3, 1, 2, 2, 2, 3, 3, 4, 2, 4, 3. You can verify that 1 appears only once, 2 appears 4 times, 2, 2, 2, and another 2, 3 appeared 4 times, and 4 appears twice. 4 appears here and here. Okay, so the number of such sequences is 11. Choose 1, 4, 4, 2, which is 11 factorial divided by 1 factorial, 4 factorial, 4 factorial, 2 factorial. And to see how you'd get it, what you do is 11 choose 1, the location of the single one, and then you'll be left with 10. So you'll do times 10 choose 4 to choose the location of the 4 2's. And now we've used 5, so instead of 11 you'd have 7. You'll have 6. 11 minus 5, 6. So you'll have times 6 choose 4, and once you do that you'll determine the sequence, and when you cancel the terms that appear there, you'll get 11 factorial divided by 1 factorial, 4 factorial, 4 factorial, 2 factorial, and you open up, you get 11 times 10 times 9 times 8 and so on times 4 factorial, and then divide by 4 factorial, 4 factorial, 2 factorial. Okay, and there's a lot of cancellations going on. 4 factorial cancels 4 factorial, and then you get the 4 and the 2 cancel with the 8 and so on, and then the 6 cancels, and that gives you this number, which is 34,650. Okay, let's look at another application. Let's look at the word Mississippi, and the question is, how many anagrams does Mississippi have? And an anagrams, as we know, is just a rearrangement of these letters that could make sense or not make sense. Okay, so what are anagrams of Mississippi? Those are just sequences over the letters MISP, sequences where the letters are M, I, S, and P in any order. So what we have is that the letter M appears once, as we see here. The letter I appears 4 times, letter S appears 4 times, and P appears twice. And perhaps not surprisingly, these are exactly the same numbers as we had in the previous slide. So therefore, the number of anagrams of Mississippi is the same as number of ways of writing sequences of 1, 2, 3, and 4, where 1 appears once, 2 appears 4 times, and so on. So it's exactly the same number. And again, the length is 11. So and one such anagram is this, and it's the same as what we've done before. And so the number of ways of doing it is going to be 11 choose 1, number of ways to choose the location of M, the number of ways to choose location of the 4 I's, the 4 S's, and the 2 P's. And that number, I apologize, that number is going to be as before, 34,650. All right, let's do another example. Students in a class. So suppose you have 10 students, and they can take a class that is given in 3 sections. They can take it in the morning, in the afternoon, or in the evening, and every student can take it any one class that they choose. They can choose morning, afternoon, or evening, but there are no constraints. So for example, if all of them want, they can all take it in the evening. So how many ways can the student take those classes? Well, clearly each student can decide whether they want the morning, afternoon, or evening, and that's true for the first student, the second student, and so on. So what we have is we have a Cartesian product. We have the product of all the possibilities, and as we said, any number of students in each class. So the number is going to be 3 to the 10, right? Because this first student can choose one of the three classes, and the second student can choose one of the three classes, and the number of possibilities is going to be 3 times 3 times 3, and so on, to get 3 to the 10. Now, suppose we are looking at how many students. We were interested in a number of ways that the students can take the class if we insist that 6 has to take the morning class, 3 have to take the afternoon class, and the remaining 1 student has to take the evening class. So how many ways can we do that? Well, now we have 10 students, and we need to select 6 of them to take the morning class, 3 of them to select the afternoon class, and 3 to select the evening class. So that number is going to be 10 choose 6, 3, 1, morning, afternoon students, and that's 10 factorial divided by 6 factorial, 6 factorial, 3 factorial, 1 factorial, which is 840. Okay. Now, this leads us in a natural way to the multinomial theorem, which generalizes the binomial theorem, and as we were going to see very soon. So the multinomial theorem says that if you take now, instead of 2 terms, a plus b and raise it to the n, if you take m terms, a1 plus a2 plus am to the n, that's going to be equal, I apologize, that's going to be equal to the summation of terms of the following, the product of at to the kt, and the coefficient in front is going to be the multinomial coefficients, coefficient n choose k1, k2 up to km. So as you remember, the binomial theorem was pretty much the same. We had a plus b raised to the n was going to be equal to summation of a to the I, b to the n minus I, like that. And then we had the binomial coefficient here, which was n choose I. Okay, so this is just a generalization. And perhaps it's easier to see if we look at raising 3 terms, sum of 3 terms to the second power. So a plus b plus c squared is going to be, according to this theorem, it's going to be summation of the multinomial coefficient 2 choose I j k times a to the I, b to the j, c to the k over all I j k that sum to 2. Okay, so this is going to be 2 choose 200 times a squared plus 2 choose 020 times b squared plus 2 choose 002 times c squared plus, and then ab, so we have to choose location of the a and location of the b. In other words, the term, we have a plus b plus c multiplied 3 times, and we choose which term we chose the a from, which term we chose the b from. So that's 1 1 and then 0 for the c's, and then plus 2 choose 1 0 1 for choosing the a and the c, and plus 2 choose 0 and 1 choosing the terms from which we take the b and the c. Okay, so we get that, and when we open them up, we get that it's going to be 2 choose 200 is 2 factorial divided by 2 factorial, which is 1, and this is again 1, and this is again 1, and that corresponds to, if we just choose if we just choose a from both locations, then we can choose it from we have to choose a from both here and from here. And likewise, if we have b squared, then we have to choose it from the first term and from the second term. On the other hand, if we look at AB, then it could come from choosing b from this location and a from b from here and a from here, or we can choose a from this term and b from the second factor. So we have 2 ways of choosing a and b. Okay, so we get that, and so this is the multinomial theorem for n equals to 2 and 3 terms. All right, so the other extension we want to talk about is sum of multinomials. So for the binomial coefficients, remember that we had the 2 to the n is summation of n choose I going from 0 to n. And for the multinomial coefficients, we'll have that m to the n, which is 1 plus 1 to the n, is going to be summation of n choose, as we just said, k1, k2 up to km, that sum to n, and all the product is going to be 1. So we get that m to the n is just the summation of the multinomial coefficients. So for binomial coefficients, we had the 2 to the n is the sum of the binomial coefficients, and for multinomial coefficients, we get that m to the n is the sum of the multinomial coefficients with m choosing m terms here. Okay, so for example, if we take 3 choose 2, m is 3 and n is 2, that's going to be, which is 9, that's going to be equal to the sum of all the multinomial coefficients, 2 choose 200 plus 2 choose 020, and so on. And you notice that these 1 and 1 and 1, and these are 2 and 2 and 2, so we get 3 plus 6, which indeed is 9. All right. So with this, we can go back to the students in the class. And you remember that we had, for simplicity, let's say we have 2 students and they take 3 classes. Then the total number of ways they can take it if there are no restrictions is going to be 3 choose 2, which is 9. Okay, if there are no restriction on how many students take the morning, afternoon, evening class. But if we break it by class, then how many ways can they take it so that both students take the morning class? That's this number here, which is going to be 1. How many ways can the students take it such that both of them take the afternoon class? That's this number here. Again, it's going to be 1. And the evening class, or how many ways can they take it so that the 2 students take it so that 1 takes the morning class, 1 takes the afternoon class? This number is going to be 2, corresponding to the first student taking the morning and the second one taking the afternoon. There are 2 ways, or this first one taking the afternoon and the second student taking the morning. There are 2 ways, and likewise for the morning and evening and the afternoon and evening. So this is going to be 1 plus 1 plus 1 plus 2 plus 2 plus 2, which gives us 9. So that's another demonstration of the multinomial theorem. Now we got 3 to the 2 is the summation of all these coefficients. All right, and so this is the same as the last slide. Okay, so what we did here was we looked at a simple extension of the binomial coefficients to multinomial coefficients and the binomial theorem to multinomial theorem. And what we're going to do next is look at another application of binomial and related coefficients.